Out there in the silent velvet expanse of the cosmos, a question hangs as old as human consciousness itself. Are we alone? This query has driven our telescopes to pierce the darkness, our equations to map the invisible, and our imaginations to journey across impossible voids. We search for life, for intelligence, for any sign that the universe is not a sterile and empty theater. But beneath this grand search lies a more intimate, a more personal quest. We are looking for a mirror. We yearn to find a place that feels like home, a system that rhymes with our own. Imagine for a moment finding not just another star, but a perfect twin to our own Sunday, a celestial sibling born from the same cosmic dust, forged in the same stellar nursery, shining with the same light, warmth, and temperament. If such a stellar doppelganger existed, what would we find orbiting it? Would we see a familiar family of planets, a small rocky world in the embrace of its warmth, a colossal gas giant patrolling the icy depths? This is no longer a flight of fancy. This is the story of a star catalogued as HD 85426. A star so uncannily like our Sun that it forces us to confront the deepest secrets of our own existence. And around this stellar twin we have found not a mirror image, but a profound and unsettling riddle. A world that shouldn't exist in our own solar system, and two colossal ghosts dancing in the dark, whose presence rewrites the story of how planetary families are born. 150 light-years from Earth, in the southern constellation of Vela the Sails, burns a point of light indistinguishable from countless others. To the naked eye, it is entirely invisible, a humble member of the galactic chorus. But to the sensitive instruments of modern astronomy, HD 85426 is a revelation. It belongs to a class of stars known as G-type main sequence stars, a category our own Sun calls home. These are the stable, long-lived hearths of the galaxy, fusing hydrogen into helium in their cores for billions of years. The classification itself is a tribute to a history of patient observation born from the work of Annie Jump Cannon and the Harvard computers in the late 19th and early 20th centuries. These brilliant women, meticulously examining photographic plates of starlight, created a system, OBAFGKM, that brought order to the celestial zoo. They learned to read the light, to see in a star's spectrum its temperature, its composition, its very essence. Yet being a G-type star is common. What makes HD 85426 extraordinary is its profound similarity to our Sunday. It is not merely a cousin, it is an identical twin. To appreciate the staggering rarity of this, consider the universe as a grand cosmic bakery. Every second, it produces billions of stellar loaves. Some are massive, hot, blue-white giants burning through their fuel in a cosmic flash. These are the giant brioches, magnificent but fleeting. Others are tiny, cool red dwarfs, the long-lasting sourdough starters of the cosmos, which will simmer for trillions of years. Our Sun and HD 85426 are like perfectly baked, golden-crusted loaves. But being a solar twin requires more than just the right size and temperature. The ingredients must be identical. This is what astronomers call metallicity, the abundance of elements heavier than hydrogen and helium. These heavy elements are the cosmic spices forged in the hearts of previous generations of stars. They are the fundamental building blocks of planets, of asteroids, and of life itself. HD 85426 possesses a metallicity that is a near perfect match to our Sun's. The recipe is the same. Furthermore, the baking time must be identical. Age is crucial. A young tempestuous star is a very different beast from an old stable one. Through a technique known as gyrochronology, studying the star's spin rate, and by analyzing its chemical makeup, astronomers have determined that HD 85426 is approximately 4.6 billion years old. It was born at the same cosmic moment as our own solar system. This star is not a glimpse into our sun's past or future, it is a snapshot of its present. Finding such a star is like finding a single specific grain of sand on all the beaches of the world. It gives us a control subject for the greatest experiment of all our own solar system. By studying this twin, we can untangle which aspects of our sun are common and which are unique. We can better predict our own star's future, its cycles of activity, its inevitable aging. With such a perfect stellar analogue in our grasp, the next question became inevitable and electrifying. What kind of planets would be born from an identical parent? The first clue did not come from a dramatic pronouncement, but from a whisper in the data, a flicker. For years, NASA's Transiting Exoplanet Survey Satellite, or TESS, has been staring unblinkingly at vast patches of the sky. Its mission is one of supreme patience built on a beautifully simple principle, the transit method. To understand this technique, imagine you are standing miles away from a colossal remote lighthouse. The lamp is blindingly bright, a constant beacon in the distance. You cannot see the intricate machinery, the cliffs it stands upon, or any ships that may be sailing nearby. All you have is that single, unwavering point of light. But then, for just a few moments, the light dims ever so slightly, then it returns to its full brilliance. Hours or perhaps days later, the exact same dimming occurs again, lasting for the same duration. You would rightly conclude that something is orbiting the lighthouse, periodically passing between you and the lamp. A moth, perhaps, circling the bulb. By measuring how much the light dips, you could estimate the size of the moth. By timing the interval between the dips, you would know its orbital period. This is the transit method in action. TESS is the observer, HD 85426 is the lighthouse, and the hoped-for planet is the tiny, unseen moth. The challenge is monumental. A planet the size of Jupiter crossing a sun-like star would dim its light by about 1%. An Earth-sized world would cause a dip of less than 1/100th of 1%. This is akin to noticing the dimming of a car's headlight when a fruit fly crosses in front of it from 100 miles away. The satellite's algorithm sifted through terabytes of data from HD 85426, searching for this faint repeating shadow. And then they found it. A signal. A periodic dimming occurring every 20 Earth days. The data was flagged, transmitted across the solar system, and pored over by scientists on the ground. Telescopes from Chile to Hawaii swiveled to stare at the solar twin, confirming the signal, ruling out false positives like star spots or background eclipsing binary stars. The shadow was real. HD 85426 was not alone. It had a companion. The planet was christened HD 85426b, and it was a complete surprise. Based on the amount of light it blocked, its size was calculated to be roughly 2.8 times the radius of Earth. This placed it firmly in a category of planet that has become one of the most fascinating and frustrating puzzles in planetary science. It is a sub-Neptune, a world larger than the biggest terrestrial planets like Earth or Venus, but smaller than the ice giants Uranus and Neptune. These are the most common type of planet we have found in the galaxy. They are everywhere. Yet in our own solar system there is a gaping hole where they should be. We have rocky worlds and we have gas giants, but nothing in between. This conspicuous absence is known as the Sub-Neptune desert, or the Fulton Gap, and the discovery of one orbiting a perfect solar twin was deeply significant. What could this alien world be like? With its 20-day orbit, it is blisteringly close to its star, far hotter than Mercury. It is not a place for life as we know it. Theories about its composition paint a strange picture. It may be a world with a substantial rocky core enveloped in an incredibly thick hydrogen and helium atmosphere, crushed under pressures we can barely imagine. Alternatively, it could be a water world, a planet with a deep global ocean, not of liquid water but of supercritical steam, a bizarre state of matter that is neither liquid nor gas. The existence of this world, HD 85426b around a star, so like our own, immediately begged the question, why is our solar system so different? Why were we deprived of the galaxy's most common planetary child? One leading hypothesis is photoevaporation. The idea is that perhaps our solar system did once have sub-Neptunes. But orbiting close to the young violent sun, the intense radiation and stellar wind would have acted like a cosmic blowtorch, stripping away their puffy atmospheres over millions of years, leaving behind only their barren rocky cores, the planets we see today. HD 85426b may be a world in the process of having its atmosphere boiled away, or perhaps it was massive enough to cling to its gaseous envelope. Studying this system, this perfect control group, offers us a laboratory to test these very ideas. But the story was far from over. As astronomers continued to watch the Sub-Neptune make its regular passage, a new subtlety began to emerge from the observations. The universe was whispering another secret. The initial discovery of the transiting world was a triumph of precision photometry. But to truly understand a planetary system, one must learn to listen for the gravitational echoes that planets leave in their wake. The next phase of the investigation moved from measuring a star's brightness to measuring its motion. This is the domain of the radial velocity method, a technique as elegant as it is powerful. It relies on a simple truth of gravity. Planets don't just orbit stars. Stars and planets orbit their common center of mass. To grasp this picture, two dancers of vastly different sizes, say a towering athlete and a small child holding hands and spinning in a circle. The child will travel in a large, sweeping arc, but the massive athlete will not remain perfectly still. They will also move tracing a much smaller circle, a subtle wobble to counterbalance the motion of their smaller partner. Now replace the dancers with a star and a planet. We cannot see the dim, distant planet directly, but we can see the star, and if we can measure its motion with incredible precision, we can detect its gravitational wobble. This is the dance of radial velocity. As the star wobbles toward us in its tiny orbit, its light is compressed, its wavelength shifting slightly toward the blue end of the spectrum. As it wobbles away from us, its light is stretched, shifting toward the red. This is the Doppler effect, the same phenomenon that changes the pitch of a passing ambulance siren. By detecting this minuscule periodic red and blue shift in the star's light, we can infer the presence of an unseen planetary partner. We can determine its orbital period by the timing of the wobble, and we can estimate its minimum mass by the amplitude of the wobble. A more massive planet yanks its star around with greater force. This method is a testament to human ingenuity. The wobble induced by even a Jupiter-sized planet is incredibly small, a velocity change of just a few meters per second, the speed of a brisk jog. For smaller planets, it's the speed of a slow walk. In 1995, astronomers Michel Mayor and Didier Queloz used this very technique to detect 51 Pegasi b, the first confirmed exoplanet, around a sun-like star. Their Nobel Prize-winning discovery opened the floodgates. And now this venerable technique was turned toward HD 85426. Using high-precision spectrographs on some of the world's largest telescopes, instruments that can dissect starlight with surgical accuracy, teams of astronomers began a long and patient vigil. They were hunting for the wobble. They knew the Sub-Neptune HD 85426b must be inducing a tiny gravitational tug. But as the data accumulated over months, then years, the signature of the star's motion was more complex than expected. The dance was not a simple two-step between the star and a single planet. There were other partners on the floor. The resulting signal was a superposition of multiple wobbles, a complex rhythm that had to be painstakingly disentangled. It's like listening to a symphony and trying to isolate the sound of a single violin while also picking out the cello and the bassoon playing different melodies. Sophisticated computer models were brought to bear testing thousands of possible planetary configurations. Slowly, a coherent picture emerged from the gravitational noise. There was not one hidden companion, there were two. The data revealed a second planet, HD 85426c, a behemoth, with a minimum mass several times that of Jupiter. This gas giant patrols a much wider orbit, taking several years to complete one circuit of its star. Its gravitational tug was the dominant slow bass note in the stellar wobble, and hiding within that rhythm was yet another signal, a third planet, HD 85426d, a world, likely similar in mass to our own Saturn, residing in an orbit somewhere between its two siblings. These two worlds do not transit. From our vantage point, their orbits are tilted, so they never pass directly in front of their star. They are gravitational ghosts, their existence revealed only by the delicate dance they impose upon their sun. Without the radial velocity method, we would never have known they were there. The family portrait of the solar twin was now complete, and it looked nothing like our own. Before us now are two families born of twin suns. On one hand, our solar system. Its inner regions are populated by small rocky worlds, Mercury, Venus, Earth, and Mars. A vast belt of asteroids then separates this terrestrial region from the outer realm of the giants Jupiter, Saturn, Uranus, and Neptune. It is an architecture of order of clear segregation between the small and the large. On the other hand, the HD 85426 system, huddled close to its star, is a Sub-Neptune, a type of world our system lacks. Further out lies a planet more massive than our Jupiter and another comparable to Saturn. The arrangement is completely different. The existence of this alternative architecture orbiting a stellar clone is a profound statement about planetary formation. It tells us that the final layout of a solar system is not solely determined by the properties of its parent star. Other factors, perhaps random chance and chaotic interactions in the system's youth, play a pivotal role. It forces us to confront theories of planetary migration. For decades, we pictured planets forming in neat circular orbits and staying there for their entire lives. We now know this view is far too simple. Planets are born in a swirling, turbulent disk of gas and dust around a young star. In this cosmic mosh pit, they can move, migrating inwards toward their star or outwards into the cold. One leading theory for our own solar system's architecture is the Grand Tack model. It proposes that in its youth, Jupiter migrated dramatically inwards, perhaps as far as the modern orbit of Mars. This inward journey would have acted like a gravitational wrecking ball, scattering smaller planetesimals and protoplanets, potentially destroying a first generation of super-Earths or sub-Neptunes that might have tried to form the inner solar system. Jupiter was then pulled back outwards by the gravitational influence of the newly forming Saturn, tacking like a sailboat and settling into its current orbit. This chaotic dance of the giants may be the very reason our inner solar system is the way it is. It may be why we have a small life-bearing Earth instead of a massive steamy sub-Neptune. Could the HD 85426 system represent what happens without such a dramatic migration? Perhaps its giants formed and stayed in more stable orbits, allowing the inner sub-Neptune to survive and thrive. This system is a fossil record of a different path not taken by our own. It shatters any notion of cosmic determinism. Two identical seeds planted in identical soil have grown into two completely different trees. This discovery carries with it a deep philosophical weight. For centuries, we have placed ourselves at the center of the universe, first physically, then biologically. Even after Copernicus, we clung to the idea that our solar system was the standard model, the default blueprint for the cosmos. HD 85426 challenges this last vestige of cosmic arrogance. It suggests that systems like ours might be the exception, not the rule. The common outcome for a Sun-like star might be a system with close-in large planets, rendering the formation of a small, wet, temperate world like Earth a rare and difficult feat. The search for another Earth just became more complex, the preciousness of our own world thrown into sharper relief. And yet the exploration of this tantalizing system has only just begun. The planets we have found are the ones that are easiest to detect. The big, the close, the massive. What else might be lurking in the shadows, in the vast unexplored spaces between these known worlds? Could there be a smaller rocky planet? An Earth analogue hiding in the system's habitable zone, its presence too faint for our current methods to confirm? The secrets of the solar twin run deeper still. The discovery of this planetary arrangement is a monumental achievement, but it is also a starting point for the next great chapter in exoplanetary science. We have found the planets, we have weighed them, we have mapped their orbits. Now we must ask the most profound question of all: what are they made of? And for the transiting world HD 85426b, we have a way to find out. The James Webb Space Telescope, a technological marvel floating 1,000,000 miles from Earth, is our eye on the universe. When this Sub-Neptune passes in front of its solar twin, a tiny fraction of the starlight will filter through the planet's atmosphere before continuing its journey to Webb's mirrors. Imprinted upon that light is a chemical fingerprint, an atmospheric barcode. Different molecules in the planet's atmosphere, water vapor, methane, carbon dioxide, absorb specific wavelengths of light. By analyzing the spectrum of the starlight after it has passed through the atmosphere, we can deduce its composition. This is the science of transmission spectroscopy. It allows us to perform a chemical assay of a world light years away. What might Webb find in the skies of HD 85426b? Given its proximity to the star, it is unlikely to be a haven for life. But discovering the composition of its atmosphere would be a Rosetta Stone for understanding this class of planet. If we find vast quantities of water vapor, it would support the water world hypothesis. If we find a primordial mix of hydrogen and helium, it will tell us about its formation in the early gas disk. This information is crucial because HD 85426 is not just any star, it is a solar twin. The light Webb will be analyzing is the light of our own sun, in effect. We understand its properties, its spectrum, its radiation, environment, better than any other type of star. This provides a clean, unambiguous baseline, allowing us to interpret the atmospheric data with unprecedented confidence. It removes a key variable from the astrobiological equation. Beyond the known planets, there is the tantalizing question of the system's habitable zone. This is the orbital band around a star, where temperatures are just right for liquid water to potentially exist on a rocky planet's surface. For a solar twin like HD 85426, this Goldilocks zone is located in the same place as our own at a distance roughly equivalent to Earth's orbit. The current radial velocity data shows no planets in this region, but our current technology is not yet sensitive enough to rule out an Earth-mass planet in an Earth-like orbit. There is a vast, quiet space in the HD 85426 system, right where a world like ours could be. It may be empty, or it may be hiding a planet that awaits a new generation of telescopes to reveal its presence. The prospect is staggering. To find an Earth-sized planet in an Earth-like orbit around a Sun-like twin It is the holy grail of exoplanet research. Even if such a world is barren and lifeless, studying it would teach us immeasurable amounts about the processes that shape terrestrial worlds. We could see what Earth might have become under slightly different circumstances. Imagine the far future, a future where we have surveyed thousands of solar twins. We will have a catalogue of their planetary families. We will be able to answer with statistical certainty which architecture is more common, the orderly layout of our home, or the strange arrangement of HD 85426. The answer will tell us about our own cosmic rarity. It will inform our search for life, guiding our telescopes toward the most promising targets. The story of this single star system will become a foundational piece of a much larger puzzle, the puzzle of our place in the galaxy. The journey to HD 85426 has taken us across light years of space and through centuries of scientific endeavor. We began with a simple point of light, a star among billions. We found in it a reflection of ourselves, a twin to our own life-giving Sunday. Around this familiar star, we expected to find a familiar family. Instead, we discovered a system that is profoundly alien, a hot Sub-Neptune where our rocky worlds should be, giant ghostly companions dancing to a different gravitational rhythm. This system is a paradox. It is both a mirror and a stranger. It teaches us that the story of a solar system is written in more than just the nature of its star. It is a tale of chaos, of chance, of migrations, and near misses in the cosmic dawn. HD 85426 holds up a distorted mirror to our own solar system, and in its reflection we see how fortunate, how rare our own home may be. It is a reminder that the universe is under no obligation to conform to our expectations. Its creativity is far more vast than our imagination. The secrets of the solar twin are not yet fully told. With every new observation, with every photon of light collected, we peel back another layer of the mystery. We will continue to watch its transiting world, to listen for its hidden wobbles, to search for new, smaller planets in the warm embrace of its light. Because in studying this distant family, we are ultimately studying ourselves. We are tracing the lines of our own cosmic ancestry and plotting a course for our future. The search goes on, driven by that same fundamental question that echoes from the dawn of our species. We look to this stellar twin and to the countless stars beyond, not just for answers, but for a deeper understanding of the question itself. For somewhere, in the light of a billion suns, lies the truth about who we are and what we might one day become.